Hi, today we'll be moving on in talking about chemical quantities, putting together what we talked about last time with, one additional step. So similar to before, we're not quite done with this. We have not effectively related mass and chemical formulas. We talked about what the molar mass of a compound is, but usually in real life you're not going to get exactly 1 mole of any one compound. You're going to go onto a scale, and like we saw in that initial video, 27.25 grams. As far as I know, that doesn't relate directly to a number on the periodic table, so how exactly do we relate grams and moles for compounds? And the short answer is you do exactly what you did for elements. So we had that conversion factor where we either had grams over moles or moles over grams, and we pick the appropriate conversion factor so that the unit we're converting from and the unit that we're converting to line up. So it's all the same process. The only difference now is that you need to maybe use a mass that is in fact the sum of masses off of your periodic table, link above. And I think in general it's going to be a good idea to not only just put a unit like we see here, but to start talking about a unit with a chemical compound so that it's 100% clear what you're representing. Just as a heads up, we're going to get into this place where we start talking about converting between chemicals. And so it might be beneficial in writing this not just to write 29.0 grams, but grams of C6H12O6 and moles of sodium chloride is, of course, NaCl. So as with before, the first step is always to write your given quantity with units, with a chemical. But I think also an early step is going to be calculating that molar mass. So you're going to have to go to your reference table. From the previous video, we know that the gram formula mass of sodium chloride is 58.5 grams per mole, and that the gram molecular mass for glucose is 180.2 grams per mole. So in both of these cases, we're converting, you have your value here, moles. So moles is going to go on the bottom of NaCl. And grams is we're asking for mass of NaCl. And then for the other one here, we're given we're given grams. So we're going to convert from grams to moles. And so again, the idea is that we set up the units initially and on the denominator to be the same so that they will cancel out. And so all that's left at this point is to plug in the appropriate numbers. And just like before, the number 1 is going to go with mole, and the mass is going to be from the periodic table, just in this case, a sum instead of just a single number. So then you just go ahead and carry out your calculations. So in these two examples, 8.1 moles of sodium chloride is the same amount as 470 grams, and 29 grams of glucose is 0.161 moles. In both cases, I'm rounding for significant figures. You don't have to do that necessarily unless the problem explicitly says it. There's one other application, one extension of this idea, and it's that you can have a situation where you can talk about moles of an element in moles of a compound. This idea of saying, well, that's great that now that before we were talking about moles to grams for an element, but now since we have that compound and that compound is made of elements, how many moles of iron are in 3.5 moles of iron 3 oxide? And to do this, you have to look at what these chemical formulas are and use them as a conversion factor in a way. And the way I like to explain this is I want to think about this third point here. It's hypothetically possible, no, it's not hypothetically possible, it's actually the case that there are 2 moles of hydrogen atoms in 1 mole of water molecules. Well, how is it possible that there's 2 moles in 1 mole? And the way I like to think about this is that if you had 5 people in a room, how many shoes would you have? The answer is, under standard conditions, 10. But how can there be 10 shoes if there's only 5 people? And it's this idea of saying if you're only talking about components of a chemical, it's possible to have multiple moles of atoms, even though you only have 1 mole of a compound. What we wrote up here in green, this is going to actually become another potential conversion factor, and this is why I think it's so important to start writing the unit with a chemical instead of just the unit. So similar to before, our first step is going to be to figure out our chemical compounds, our formulas. So iron, that's Fe2O3, and aluminum chloride, that's AlCl3. If you need to go back and review where that came from, there's a couple videos a unit or two ago about naming. This will be pretty beneficial here because we're going to have to relate back using this. This is an idea of 2 moles of iron to every 3 moles of oxygen, or to every 1 mole of compound. And then here it's the same, where we have the idea of, and I'm going to write that. There's 1 aluminum for every 3 chlorines for every 1 aluminum chloride. And so that's going to build our other piece. So same as before, write our given value. We're going to convert, so moles of iron oxide on the bottom and grams of aluminum. And for the top one, our target here is moles of just iron. So we're going to go back to what we wrote up top here, and we're just going to pick out the numbers that correspond to what we're talking about. There's 2 irons for every 1 Fe2O3, and so in 3.5 moles of iron oxide, there's 7.0 moles of just iron. For this second problem here, we're given a gram value initially, so before we make this conversion, notice that we have to start with moles. There's only a relationship in terms of moles because, of course, moles is based on particles. You can't compare particles to grams directly, just like before. And then we're going to have moles of AlCl3. And then again, just like the previous problem, we're going to have our moles of compound on the bottom, and our target is just moles of chlorine. So from our numbers, this is going to be a 3 and a 1, and then I'll really quickly calculate 133.3 grams, and then calculate out. And our final answer here is 1.26 moles of chlorine atoms. I understand that you might be thinking, but wait, isn't that Cl2? Since we're talking about elements in a compound, not elements existing as elements, that diatomic rule is no longer valid. It depends on the compound. And so we can talk about just single atoms, even though like they're unbonded, even though they're not. So to sum things up, the molar mass is now a component of your conversion factor. So it's good to have just not only just the unit, also the formula in your dimensional analysis. Since the moles refer to a number of objects, and there's a number of objects in your compound, it's possible to have multiple moles of an element present in a certain amount of a compound. In this way, this is now the first time we're going to see that case where usually we write this 1 every time we write the unit moles. That's only really the case when we're converting from grams to moles or moles to grams. If there's a conversion within a chemical compound, that might not always be the case. Sometimes there's a number other than 1. The one final thing I'll say is that everything we've done here today deals with only one chemical. So the whole process of using balanced chemical reactions and coming up with coefficients does not apply here and should not be applied here. Thanks for watching.